Hello everyone, my name is Amir Hossein Madadi from Department of Civil and Environmental Engineering at University of Massachusetts Lowell, and my presentation today entitled Deterioration Evaluation of Reinforced Concrete Materials in Highway Bridges. For your introduction, this research endeavors to detect and monitor the degradation behavior of concrete in New England's highway bridges through meticulous characterizations of field-collected samples and accelerated aging tests in the laboratory. Our focus lies in understanding the evolving components, reaction products, and chemical bonds in aged materials, with the final goal of developing comprehensive data for a thorough condition assessment. The primary objective of this study includes conducting a rigorous condition assessment of existing infrastructure through multiple material characterizations, and also to gain insight into the development of reaction products and chemical bonds in aged concrete materials. To achieve these goals, we selected 4 locations on 3 different reinforced concrete piers of the I-495 bridge in Chelmsford, Massachusetts. As you can see in figure 1, locations 1 and 2 are shown at part A and B. Actually, the enlarged parts of these locations are shown in part B and C. And at part D, we can see all the other locations, the piers of this bridge, but due to the limitation of the time and space, we only selected 2 locations here to present the results based on those locations. Also, at part D, you can see an example of the collected samples. We usually, for these samples, we collected the samples actually based on a monthly frequency, and then the materials went through the characterization by using X-ray diffraction or XRD, thermogravimetric analysis or TGA, and Fourier transform in infrared spectroscopy. And the results are analyzed and shown here. As you can see in figure 2, the results of X-ray diffraction analysis of the samples collected sometime between the September of 2022 and October of 2023 are shown here. As you might know, X-ray diffraction analysis is a non-destructive technique that provides detailed information about the crystallographic structure, chemical composition, and physical properties of a material. Based on the XRD pattern and the quantification analysis based on Rietveld refinement, it can be seen that quartz and calcite or calcium carbonate are the main crystalline components of the samples, where we can see also a gradual increase in calcite over time, which can be seen based on the quantification analysis, which is shown in part B of this figure 2. Also, from this XRD result, we can detect the iron oxide as another phase, and it is likely a result of rust in collected samples, which is due to the corrosion of reinforcing rebars. The overall increasing of this phase also suggests an ongoing corrosion in the reinforced concrete bridge piers. The results of thermogravimetric analysis or TGA is also shown in figure 3. TGA is a powerful technique for the measurements of thermal stability of materials. In this method, changes in the weight of a specimen are measured while the temperature of the sample is increased. Figure 3, part A shows that weight drops at different temperatures, and part B indicates the first derivative of TGA curve. In order to better understand the decomposition patterns, and the table below provides the quantification data of the different phases. Based on these results, the main findings indicate that the increases in CSH or calcium silicate hydrates, and also the CO2 content of the samples over time, which shows the ongoing reaction within the concrete materials of the bridge piers. Next analysis that we have done in this study is Fourier transform infrared spectroscopy, which is used to identify the molecular compounds, and it works by measuring the absorbance and transmittance of the infrared radiation by a sample. The resulting spectrum can then be used to identify the functional group and chemical bonds which are present in the material. In figure 4, our FTIR spectra indicate the increases in the intensity of the SiO bond at, for example, 1010 centimeter inverse, and also the FeO bond, FeO stretching at 527 centimeter inverse. These findings align with the elevated CSH content and iron oxide content which are observed in TGA and XRD data. This FTIR analysis also shows some carbonator related shifts, as you can see in figure 4, at different wave numbers, for example at 710, 875 and 1417 centimeter inverse. The increasing of the intensity of these shifts also signifies the progressing carbonation in the aged regions, which can show the potential risks of the further degradation to the reinforced concrete structures. In conclusion, our study provides valuable insights into the deterioration of concrete materials in highway bridges. The main crystalline components, as quartz and calcite, in the XRD analysis show a gradual increase over time, which is the indication of ongoing degradation in the reinforced concrete materials. The XRD, TGA, and FTIR analysis all can show the increases in CSH content, carbonation products, and rust content, suggesting the corrosion in the reinforced concrete bridge piers. These findings contribute to a more informed approach to condition assessment and lay the foundation for future strategies in maintaining the integrity of highway bridge infrastructures. Thank you for your attention, and I'm open to any questions you may have.